This is the E-module designed for the West Bengal State University syllabus according to this syllabus for chemistry honor students for Sem II. This is a core course 3 and the paper code is CENA-COR03T. So welcome to this E-module. I am Dr. Moumita Biswas, Assistant Professor from Parakpur Rashtraguru Shridharnath College. Now we are going to our first slide. This is Hund's rule. Now what is Hund's rule? Now Hund's rule is basically a rule according to which the electrons is entering into the orbitals. You can see the 1s orbital, then the 2s orbital. Okay. Now we are going to explain this Hund's rule for the 2p orbital. Now you see there are 3 orbitals. We know that 2 in p, px, py and pz. So when one electron is entering, it choose any one. Then the second electron when comes, then there is a question whether it is in this orbital or choose any other orbital. So according to Hund's rule, the electron choose the other orbital and it is in the same spin because for the least repulsion of inter-electronic repulsion. Okay. So the electron choose as enter in the orbital so that it enjoys the most space and feels the least inter-electronic repulsion. So now when the third electron comes, it choose the third orbital. And when all the orbitals is the half filled, then when the fourth electron comes, it choose any one and then it is pairing. So according to Hund's rule, it's first the electron comes as unpaired. When it is half filled, then it is paired. Okay. And when it is come for the half filled, then all the spins are parallel. So this is the Hund's rule. Okay. Electrons entering in the p orbital. I explain this Hund's rule by this example. Okay. So this is the Hund's rule. Now we go to the next slide. So this is very important thing, quantum number of electrons. We can define any electrons as their quantum numbers. We know there are 4 quantum numbers for electrons. First one is the principal quantum numbers, which is assigned with the N. Then the angular momentum quantum number, it is also called the azimuthal quantum number. It is assigned with the L. And then magnetic quantum number, it is assigned with the M. And then spin quantum number, it is assigned with the S or MS. Okay. Now, we know the principal quantum number. Principal quantum number comes from the Bohr's theory, and principal quantum number means n equal to 1. That means for first orbital it is 1. For second orbital it is 2. For third orbital the principal quantum number is 3. So actually principal quantum number means the number of orbitals. Okay. Then the azimuthal quantum number or angular momentum quantum number L. This L depends on the principal quantum number. Okay. I show here as it is the L starting from 0 and ending with n minus 1. That means if the principal quantum number is 1, then the azimuthal quantum number N will be 0. Okay. Because we know that 1 minus 1 is 0, so N will be 0. So when N equal to 1, we know that the L value is 0 to N minus 1. So for N equal to 1, N has just one value, N equal to 0. For N equal to 2, N has two values, 0 and 1. Okay, and so on. For N equal to 3, N has the value 0, 1 and 2. Okay. So we can see the azimuthal quantum number depends on the principal quantum number N. If we know the values of principal quantum number, we can know the values of the azimuthal quantum number because it depends on the principal quantum number. Now the third quantum number is the magnetic quantum number N. This N depends on the N. N value is minus N to plus N. Okay. So now you can see if N equal to 0, then N has just one value 0 if n equal to 1, then n has value -1, 0 and +1. Okay, because the value of n is -n to +n. Now if n equal to 3, then n values are -3, -2, -1, 0, +1, +2 and +3. These are the values for magnetic quantum number. Okay, so magnetic quantum number depends on the L, and so magnetic quantum number also depends on the N, because L depends on the N. So this magnetic quantum number and the azimuthal quantum number both depends on the principal quantum number N. Okay. Now the last quantum number of electron is the spin quantum number. This spin quantum number has just two values, that is +half and -half. Okay, and it is independent. It does not depend on any quantum numbers. It has just two values, +half and -half. So by these four quantum numbers we can assign any electron of an atom. Okay, so there are four quantum numbers: principal quantum number, azimuthal quantum number, magnetic quantum number and the spin quantum number. Principal quantum number means the orbital number. Azimuthal quantum number is 0 to n-1, and the magnetic quantum number values is -n to +n, and spin quantum number values are +half and -half. Okay, with these four values we can define any electrons of an atom. Okay, now we go for the next slide. Okay, this is Pauli's exclusion principle. Pauli's exclusion principle said that no two electrons in an atom can have the same set of four identical quantum numbers. So we can prove this. We can prove with these values. Okay, how we can prove the Pauli's quantum number? Let's take an example. Let's take an example. Is it possible that two electrons have four identical quantum numbers? Is it possible or not? According to Pauli's exclusive principle, all the electrons are exclusive. All the electrons have a unique set of quantum numbers, and it does not fully match with the others. Okay, therefore they are exclusive. So now let's check. Is it possible? Now for n equal to 2, how many electrons possible for n equal to 2? Okay, so principal quantum number is 2. So L, according to our previous talk, n equal to 0. The values of possible is 0 and 1. Okay, so this is a set for n equal to 2. N has two values, 0 and 1. And n equal to, first we take this set. First we take this set. Okay, that when n equal to 2 and n equal to 0, this set of electrons. So when n equal to 2 and n equal to 0, we have n equal to just one value 0, because L is 0, and we know n has -n to +n value. So as 0, n equal to 0, so n will be also 0. S will be possible, S is +half and -half. So there are two electrons possible, two electrons, one set of electrons, this set, that is one electron has n equal to 2, n equal to 0, n equal to 0 and S equal to +half, and another electron is, the set is n equal to again 2, n equal to 0, n equal to 0, but the spin value is different, that is -half. So they are not identical. Here it is changed. Their spin values is changed. Now take this one, that is n equal to 2 and n equal to 1, this value. So for this we have n equal to -1, 0 and +1. Okay, and for each of these we have a set of S value is +half, -half. Here also +half, -half. Here also +half, -half. So we have 1, 2, 3, 4, 5, 6 electrons. Okay, so all have something is different. Okay, so it is not possible when you take these sets is different, these sets are different, all are different. Okay, so we don't find in an atom, 2 electrons which has 4 the quantum numbers, all the quantum numbers identical. It is not possible. So this is the Pauli's exclusion principle. That is, no 2 electrons in an atom which have all the identical quantum numbers. It is not possible. Okay, so all the electrons in an atom are exclusive. It is the Pauli's exclusion principle. Now we will go for the next slide. This is very interesting. This is radial distribution function of orbitals. Radial distribution function of orbitals. Now we see some schematic diagram. This is radial distribution function for 1s and this is for the 2s. Okay. So this is, if I show here, this is the radial distribution probability of finding the electron. Here this is the radial distribution function. Okay. So this is for the 1s orbital. Okay. And this is for the 2s orbital. Now if I plot this one in a same figure, then it will be like this. This will be for the 2s orbital. Okay. So we can see there is sum of electron density is into the 1s orbital. Okay. If you plot the both here, 1s radial distribution function of 1s and 2s, we can see sum of electron density is into the 1s orbital. The area of 1s orbital. This is called the penetration. That is, all the electron density is not out of the 1s orbital. Some of the electron density of 2s orbital is into the 1s orbital's area. This is called the penetration. Okay. Now we see this one in this picture. Okay. There is a 2p orbital and 2s orbital. Here also we see there is a penetration. Okay. Now this is a comparative radial distribution function of 1s, 2s, 3s and 4s orbital. So if we take here 1s and 2s orbital, you can see this is 1s orbital, this is 2s orbital, this is 3s and 4s. We see that some portion of the consecutive orbitals is in the area of previous orbitals. Okay, so electron density is penetrated. This is called the penetration. And this penetration tendency is like this. S orbital has the maximum penetration, then P, then D and then A orbital. This is the order of penetration of orbitals. Okay. So this is the radial distribution function of orbitals. Now we move on to the shape of orbitals. Now shape of orbitals. All the orbitals have distinct shape. We can see here first. This is the S orbital, spherical shape, then the P orbital. Okay, and we see the spherical shape orbital is a symmetrical orbital. Okay, X, Y, and Z. This is the symmetrical orbitals. S orbital. Then the PS orbital. We can see it is X. Then PS orbital is along the X orbital, X axis. So it is called the PX orbital because it is along the X axis. And we can see Y orbital is along the Y axis and Z orbital is along the Z axis. So it is the name is according to their alignment. Now next is the D orbital. These are the D orbitals. Okay, we have this dxy, dxz and dyz. They are the similar kind of orbital. The shape is similar, and then dx square minus y square. It is also quite similar with this orbital, and then dz square orbital. Okay. So these are the 5 kinds of d orbitals. The shape of the d orbitals. And then this is a very interesting. This is ground state term symbol. We can assign the ground state term symbol How it's possible? Okay, how it is possible? Let's check first here. Here I solved some of them, and you can see like P2 orbital. We explain with the P2 orbital. Okay, we are going to find out the term symbol for P2 orbital. Now we know this P orbital has three orbitals actually, Px, Py, Pz, and for P the L is, because three orbital, because the azimuthal for L is 1. For any P orbital L is 1, and the M value, you know, the M value is -1, 0 and +1. Okay, so here it is +1. M value, azimuthal quantum value is +1, 0 and -1. Okay, so this is the azimuthal quantum value, +1, 0 and -1. And then you take the 2 electrons here, 2 electrons. Okay, and now we summation of M is here +1 + 0, that means +1. Okay, summation of M is +1. So the ground state term symbol, we are going to find out the ground state, because it is ground state, not excited state, it is just ground state. Here ground state term symbol. Okay, term symbol. Now the symbol depends on this value, this summation of magnetic quantum number values. Okay, if this summation is 0, then our symbol will be S. If summation is 1, then it will be P. And if the summation is 2, then it will be D. Okay, if the summation is 3, then it will be F. Okay, this is the symbol for the term symbol for the ground state. Now you can see here the summation is 1, so the symbol will be P. So for the P2 configuration, the symbol, term symbol will be P. And now we put here, it is 2s plus 1 and it is J. Now we explain what is 2 plus 1. S means the spin value. Here we have 2 spin, so the summation of spin is 1. So 2s plus 1, this value will be 2s plus 1, this value will be 3. So ground state term symbol, you put here 3 because S is 1 and 2s plus 1 will be 3. So it is 3p. Now what is J value? J means L minus S. Okay, J means up to less than half field. For less than half field, J will be L minus S. And for greater than half field, J will be L plus S. Now it is less than half field, so the J value will be L minus S. Here the L value we can see, L value is 1. So and S value is 1. So here J equal to 1 minus 1 equal to 0. So here we put here 0. So the ground state term symbol for P2 is 3p0. Okay. Now this is the ground state term symbol for P2. Now if it is D3, then what will be the term symbol for D3? Now we put, or D6, anything. Now we explain, if it is D3, then what will be the term symbol for D3? Now we put here D3, that means we know the 5 orbitals, D has 5 orbitals, it means always D equal to N equal to 2. So the N values will be, there are 5 N values, -2, -1, 0, +1, +2. Now if we follow the Hund's rule, so the 3 electrons entering like this. Okay. Now we sum the M values, that is -2, -1, 0. Okay. So we take this value, we take the mod value actually, it is 3. So M values is 3. Now we know if M equal to 0, then our symbol will be S. If it is 1, then our symbol will be P. If it is 2, then our symbol will be D. If it is 3, then the symbol will be F. So here the symbol will be F. Okay? Symbol is F. Now here we know 2s plus 1 and J. And now 2s plus, what will be the S here? A summation of A is equal to, you can see, half plus half plus half, that means 3 by 2. So 2s plus 1 will be 4. So here it is 4a. And what will be j? As it is less than half filled, so j will be L minus s. L is 2. So minus s means a summation of s is 3 by 2. So what will be 1 by 2. This is j. So our ground state term symbol will be 4a half. This is the term symbol, ground state term symbol for J3. Okay. So this is, by this method we can find out the ground state term symbol for any configuration. Okay. Now we go for our next slide. So this is all about the today's class. Today we are discussing about the Hund's rule. Okay. Number 2 is the quantum numbers of electrons. Quantum numbers, and then the radial distribution of orbitals, radial distribution function of orbitals. Okay. So first we discuss about Hund's rule, then quantum numbers, then radial distribution functions of orbitals, then shape of the orbitals. I missed something here. Before it, we discuss the Pauli's exclusion principles. Pauli's exclusion principle. Okay. Number 4, radial distribution function of orbitals, then shape of the orbitals, and then at last, the last point is the ground state term symbol. Okay. Ground state term symbol. Okay. So this is the references. It's very, it's very popular books of inorganic chemistry. These are references. You get all these topics from here. And then this is a small feedback. This is small questionnaire for you. First one, explain the Hund's rule with example. Number 2, what is the Pauli's exclusion principle? Number 3, draw the shape of d orbitals. Number 4, explain with schematic diagram of radial distribution function of 1s, 2s and 2p orbitals. And the last one is the find out the ground state term symbol of P2 and D6 configuration. This is the feedback for you, and you can send this to my mail ID directly. That is my mail ID, moumita@gmail.com. Okay. Now